Okay, today we're talking about making sense of statistical significance and what does it mean? So, we talked about there being different alpha levels or different significance levels. Point 0.1, 0.05, point 0.01. So how do you choose? Well, it depends how plausible H naught is. Okay? If H naught seems likely, you probably want stronger evidence against it. So you'd choose a lower alpha level. Null hypothesis. That's the assumed case. That's the no change. Um, and it also depends on what are the consequences of rejecting H naught. If rejecting H naught means, well, I'm potentially giving you a drug that's going to kill you, you're going to use a low alpha level. Okay? If the consequences of rejecting H naught are, well, this Spanish learning program isn't going to actually help you any more than the original, the consequences aren't that high. You go, oh, well, it wasn't actually any better. Um, that makes sense. You probably, with that case, you'll probably use a much higher alpha level, maybe like a 0.1. If it's two-sided, because you're doubling for the two-sided, you might use a twice as high of an alpha level, potentially. Feel like it's one-sided, but I want it to be pretty tight. It's not common to use 0.025, but you could. So here's one that I like. Wound healing time. Suppose we're testing a new antibacterial cream called Formulation NS on cuts made on the inner forearm. We know that the previous research that with no medication, the healing time is 7.6 days. So instead of doing a control group, this was already done. They already had this data. So the control group data was already done. Um, and the standard deviation of 1.4 days. We claim we want to test here that formulation NS speeds healing. We'll use the 5% significance level. So we cut 25 volunteer college students and apply formulation NS to the wound. Those 25 volunteers, I'm sure, are getting paid. In college, yes. The mean healing time of these subjects is 7.1 days. We will assume sigma is still 1.4, which is a reasonable assumption. Okay, so H naught, mu equals 7.6. We're assuming it's the same. HA mu is less than 7.6. We're also assuming that formulation NS does not slow down healing. If it doesn't speed it up, we won't use it. If it slows it down, well, that would be the same effect as not speeding it up, so we don't need to do two-sided. Does that make sense? So, choose the appropriate inference procedure, verify the conditions. We know sigma. We are willing to treat our 25 subjects as a SRS, even though they are volunteers, because there's no reason to assume that they would be different from the population of interest. Which I suppose our population is college students in this case, or young adults. So you could not generalize this experiment to older adults, but there's reason to believe it probably would. Like the reason they do it on college students is they're right there. I'm not going to drive down to ISU to get my cut and apply my healing every day. Versus an ISU kid, yeah, you're gonna cut and apply this. I need to come in once a day for a week. You'll give me $100. Sure. And we would need to check for normality. It only needs to be somewhat normal. No real strong deviations or outliers. They don't give us the data, so we can't actually do the check. So we run it through this, and I'm going to show you how to do this on the calculator. I do not need to enter my data because I don't have data. I'm going to do menu, statistics, stats test. You can do this in Scratchpad. You're going to do statistics, stats, tests, and this is a z-test. Anytime we know sigma, we're not going to enter data, we're going to enter stats. Z-test. We're calculating a z. So mu naught, 7.6. That's my h naught value. Sigma, 1.4. X bar was 7.1. My sample size was 20. I'm looking at mu is less than mu naught. Tell me when you guys have that. Everybody may understand how I got where I got all those numbers from the problem. Well, this is going to give me my z. So your formula would have given you negative 1.785. But it also gives me my p-value of 0.037. That's pretty nice, huh? So it did it all in one step, no table needed. Yeah, you could have if you calculated the z by hand, you can do distributions, normal CDF. You always do CDFs on these. Or inverse normal if you have the area and you're trying to go backwards. So you do need to get used to that because you're not going to get the tables on the test. So step 3, I would probably on your exam, I would write the formula. I'd write, oops. Okay, I would write z equals, and then I'd do the 7.1 minus 7.6. And then I'd write the value it gave me next to it and write p-value next to it. So as you're showing your steps, so I would actually write that formula. I would not do that for 2-sample because it gets a lot more complicated. But so then step 4, interpret the result. Since my p-value is less than 0.05, I'm rejecting H naught and concluding HA, which means formulation NS does speed up healing time. Here's the thing though, it sped it up by a half a day. Are you going to put this on twice a day and go to the store, buy it, put it on twice a day to speed up your healing of a cut by half a day when it still takes a week? So sometimes things are statistically significant. That's like what not worth actually doing, not practically significant. Okay. Don't confuse the two. I can tell you there's one on your next test. I don't know if there'll be any of that on the IB test, but they want you to know and be able to know and interpret. That could potentially be a useful thing in your bio IA. If you're like, yeah, this is statistically significant, but it's still a kind of small number. Or so you can speak to that at the end of it. This seems to be enough to make be worth going and getting this different soil treatment or whatever. Or I'm not convinced that this was worth is worth doing if I was doing in a regular case. Okay. Next example. Statistical inference is not valid for all sets of data. This is called the Hawthorne effect because it was seen in a, I think in a city called Hawthorne. So you wonder whether playing background music would improve productivity of staff who process mail orders in your business. So playing music for people doing menial, repetitive jobs. After discussing the ideas with the workers, you add music and find a significant increase. You should not be impressed. In fact, almost any change in the work environment, together with the knowledge that a study is underway, will produce a short-term productivity increase. That's known as the Hawthorne effect, named after the Western Electric manufacturing plant where it was first noted. Significance test correctly informs you of the increase has occurred, and it's larger than by chance alone. It does not tell you what other than chance caused the increase. Okay, that's an important thing. Significant test doesn't tell you what caused it. That needs to be in your experiment design. And if you offer something that people want with the knowledge that they're being watched to see if it helps, it will help almost for sure in the short term. Even if you just tell them you're being watched, it will help in the short term. Your productivity is being evaluated. Predicting successful trainees. You want to learn what distinguishes managerial trainees who eventually become executives from those who, after expensive training, don't succeed. And who leave the company. You have abundant data on past trainees, data on their personalities, goals, their college preparation, and performance, even their family backgrounds and their hobbies. So, statistical software makes it even easier than your calculator to run test after test after test. You should expect something that isn't significant to show up as significant. Because 5% of the time, things show up as significant by chance alone. Does that make sense? So if you run 50 significance tests that mean on data that means absolutely nothing, you should get 2 or 3 of them to say, oh, this is significant on average. Average of 2.5, I think. If you did it 100 times, you should get an average of 5 data points to be significant when they're not significant at all. That makes sense. Significance tests don't guarantee you that your results are true. It happens by random chance, whatever your significance level is. Okay. One really quick thing, and then those of you that have to go have to go. Type 1 and 2 error. Type 1 error means you reject H naught when H naught is actually true. That is simply your alpha level. So you've concluded HA, but HA wasn't true. It just was far enough away by random chance. Because you get something in that distribution. Sometimes it's on the ends of the distribution. Maybe it is truly here at 0, but your data, you just happen to get a high sample. The probability of a type 1 error is your alpha level. Okay. Usually that's 0.05. It could be 0.01, but it's whatever you set that as. So if you remember, we didn't conclude H naught, we failed to reject. But essentially, in practical, when you're making decisions, you fail to reject, you're borderline concluding. Yep. Yep. Okay. Can I have 30 more seconds? Type 2 error is when you fail to reject H naught, which means you effectively concluded it when HA was actually true. Okay. Your evidence wasn't quite strong enough for you to conclude HA, but it was true. Type 1 error is easy to calculate. Rejecting H naught when HA is true is the correct decision. Failing to reject H naught, which effectively means accepting H naught when H naught is true, is a correct decision. Again, you still have to consider the practicality, but those are correct decisions. Okay? You guys are going to have to watch this video. You got this, Dylan.
Like I look you like the feeling when you're about to run like your 100 meter? It's like that kind of
The feeling that when I'm about to run my 100 meter, can I beat anybody? Can I beat anybody? Can I get under 16 seconds? The answer now is no. In high school, I think I could have got under 16. For boys, for girls, 14 would be good. Really good is in the 12s.
okay, but that's like winning state.
No, it's not. Like 12 flat is like winning state.
Uh,
Or 11, 8.
I don't want to love I ran like a 12.6.
Yeah.
I'm probably like I'm focused on long jump for better shot. So
I guess I need to mark Izzy absent, not tardy. Yeah.
I rewrote my essay basically, but it's so good. It's so much better. I just had it from a utilitarian perspective. Like,
Okay. Yeah. I'm like, I hope that means it's actually better.
So. That's behind. You don't need to start that yet. Well, I've done research though, but I just don't know if there's like the right kind of.
I'm not sure he started his research till after Christmas.
He said. I've been in your. That's how he wrote it.
Okay. So error probabilities. Are these chips too salty? So one of the really important things, if you're running a business, if your chips are too salty, no one's going to buy them. They're not good. People will stop buying them. They'll move on. If you're releasing bad batches of chips. If your chips are the right saltiness, but you conclude they're too salty, you throw out a whole day's worth of chips. Both of these are bad. Okay. So you don't want to make either type of error. Consequence of the type 1 error is you threw out good chips, you wasted a lot of money. Consequences of the type 2 are you sold bad chips, and you're probably going to lose customers. So you have decided, as the chip manufacturer, that the proper amount of salt is 2 milligrams. I think that's per chip. The standard deviation from testing your chips regularly is 0.1. This is a two-sided, because if our chips are not salty enough or too salty, they're not going to taste right. So this is a not equals case. And we're going to use the 5% significance level. So calculating a type 2 error might be the hardest thing in stats. Once it clicks, and what I've seen of this on the IB is actually easier than this particular calculation. They like to do it with binomial, but it's the same idea. You're going to pick, and we're going to do this. If you can do this, you can do it with binomial. You can do what's on the IB test. And there's a couple of steps to it. So there's a couple of keys here. Remember that if it's 2, your data will fall somewhere within a distribution. So this is my data. When calculating a type 2 error, you must decide a value that's far enough away that I would want to reject. So it's a practically significant value. And the chip manufacturer has decided that 2.05 is the chips are salty enough that they just don't taste quite right. So notice that there is some overlap in these distributions. If it's actually 2.05, we could get a sample that's low sodium or low salt content. And my whole batch was 2.05, but my sample came out on the low side. And we get this overlap here. Right here. This pink part. That's not the greatest color here. It didn't change. Or now it's going to be this lighter blue. That overlapping area is the probability that it was actually 2.05. I got a low salt sample and it fell within the part that I would accept. Yes, theoretically, your curve could go all the way over here. That probability is essentially 0. Now, if I repeated this with a 1.95, I'd get an exactly mirrored thing and I'd get the same probability. So if it's off by 0.05, either way, I will get the same probability that I screwed up. That makes sense? So to calculate this, we can calculate a type 2 error. One of the things, a confidence interval, when you're doing a significance test, if your X bar falls within the confidence interval for the H naught, you would accept. If it doesn't, you'd reject. So what we're going to do to start with is make a confidence interval. And I do not like how they notate that, but we had H naught mu equals 2. HA mu is not equal to. So this is a two-sided test, which means 5% significance level is equal to a 90% confidence interval. 95. Because confidence intervals are two-tailed. If it was a one-tailed, a 5% significance level would be a 90 because 5% on each side of the confidence interval. But because it's two-tailed, confidence intervals are all two-tailed. So I calculate my confidence interval. 2 plus or minus Z star for 95% is 1.96 times sigma 0.1, yep, over square root of 50. And that gives me these. 1.972 to 2.027. And you could do that confidence interval on your calculator if you're not remembering Z star or whatever. But it's probably good to memorize those kind of 4 or 5 Z stars. So now what I'm going to do is I'm going to run my Z test with 2.05. My new Z minus, I'm going to use my upper level. Because as I look back on this, that's the overlap. Yeah, my lower one is, what's the probability that this area right out here, and it's basically 0. It's so small that I can assume. The 3 sig figs, it's 0. When you subtract it, it won't affect that. So I'm looking at this. This is my 2.027. Let me write that in a better spot. No. So that's why I'm going back here. This value right here is 2.027. That's 2.05. So when I do my calculation, my mean is 2.05. I got that backwards. My mu is 2.05. My X bar is 2.027. And honestly, if you get it backwards, you'll just get a mirrored thing. 2.027 minus 2.05 over my standard deviation and sample size didn't change. So I'm going to show you how to do this. I can calculate this. Well, let's just calculate it on the calculator. Let's not try to use the stats test. I think it's going to complicate things. .027 minus 2.05 over 0.1 divided by square root of 50. And I get 1.6235. I'm going to get rid of some of this stuff. And I'm going to write that value down. So as I'm showing my work, I'd show that out, that calculation. I'd have Z equals negative 1.62635. I'll just leave a lot. And then I'm going to do menu, statistics, so this is effectively looking it up in the table right now. I'm going to do distributions, normal CDF. Lower bound. Because I'm looking at my curve as if it's this side is where my overlap was, my lower bound can be this at what's effectively negative infinity. Usually, if I'm doing it, I just enter like 10,000. it's close enough that to the significant figures you're supposed to round to, you're not going to change it. I usually do negative 10,000 or positive 10,000. My upper value is negative 1.626. I'll just do all of them. My mean is, if I put it through Z, my mean is 0, my sigma is 1. The Z calculation standardizes everything to a mean of 0. That's what it's doing. There's a way that you could put it in without actually doing the calculation, but I don't think it's actually easier. You get 0.052 or 0.0519 or 5.19% chance of type 2 error. We had a 5% chance of type 1 error, 5.19% chance of type 2 error. That's pretty good. We can probably conclude that our sampling is good enough. Most of the time, our chips are going to be good. Yes, there is a possibility we'll sell a bad batch. If the batch is worse than 2.05, the possibility goes down even further. Okay. But you ideally want to pick that value at 2.05 at the saltiness that you start to notice. Like, oh, these aren't quite as good, or 1.95. Again, it's mirrored on the distribution. So 1.95 and 2.05 are going to give you the same values. It's also going to be taste weird. Yep. And you kind of pick it at this is where we start to notice. And these are going to be your expert tasters. These are the people that came up with the recipe and said, oh, this is what we want for our chips. That kind of makes sense on type 2 error. Actually executing the calculation is the hard part. Yeah, if you can get the concept, we can get you to execute the calculation. There's a video on how to do a couple of them. I recorded it last year when going through an example. Like, if you get to the problems and you get stuck, I think it's 10.7.3 and 10.7.4. Watch it. I'll go through it. I don't have time to go through it in class this year, unfortunately. Yeah, we're just too behind. I don't even know how we got behind, but we did. Okay, one more thing, and this is applying type 2 error. It's if you can calculate the type 2 error, this part is easy. They got it. Oh, they rounded off a little more than I did. Oh, no, they rounded off less here. Did I round off too much in that? Did I round incorrectly? I might have rounded incorrectly.
I think you did 2.02.
2.0277. Oh, I just looked at what they had in that one spot because I didn't actually calculate that out. So yes, you got a little higher from rounding. If you show your work and you did at least, well, they actually want you to carry more than 3. You only have to write out 3, but you need to carry more than 3 in your calculator. So that's a good, you probably wouldn't get the point on that. You get all the rest of the points, but not the answer point. And if you had to use it later, they would give you what's called follow-through points of you had this wrong answer, but you used it correctly. You did the work correctly. You got a wrong answer because you inserted this number where you rounded wrong earlier. They'll probably ding you a point, not all of them. They're trying to give you points where you know the stuff. Hopefully that's reassuring. They're not actually out to get you. It might feel like they are because the questions are so hard, but okay, power. Power is simply 1 minus type 2 error. What it means So effectively, we had a 0.05 alpha level. That means we'll make the right decision on whether to reject or not 95% of the time. The power is the percentage of if it is this far off, will we make the correct decision to reject? And so my power was 1 minus, I think it was 0.057. We'll say 0.0571. So this is power equals 94.29%. Or 90 to sig figs 94.3. So yeah, it means if the chips actually are bad 94.3% of the time, we're going to find it. It's not quite 95, but the generally accepted power is anything over 0.8 or 80%. So usually the generally accepted reject rule is 0.05, or you'll get it right 95% of the time. And the power generally should be 80% is what's generally accepted. If you can get over that, you're performing a pretty good test. You cannot, there is no way, this is stats, and stats is about analyzing what would be random. You can't guarantee anything with any test. There's always that one chance that you selected 50 people and you selected the 50 most extreme people in your sample by randomness. It's super ridiculously highly unlikely, but it is possible. So, ways to increase a power. Okay, well, we're going to do one more example. We're going to calculate the type 2 error. And then we'll talk about ways to increase the power. So, can a 6-month exercise program increase the total body bone mineral content of young women? I have a feeling this is about helping prevent osteoporosis later. Yes, it's definitely later in life thing, but I think they're going, can exercise help you be less susceptible later in life? Exercise when you're young, because that usually would convince some people to at least do a little more. So, based on the results of a previous study, we are willing to assume that sigma equals 2 for the percent in total body, whatever, over a 6-month period. A change in TBMC of 1% would be considered important, and researchers would like to have a reasonable chance of detecting this change. Is 25 subjects large enough? I think the answer is actually yes. We'll see for sure. I don't remember for sure. But so step 1, we're going to state our null hypothesis. We're going to essentially set up what we're going to do a test. You should do step 2 and verify the conditions, but you can't do step 2 yet to verify normality because you don't have your data. So this is in the planning stage of, we're going to run this test. Is 25 actually big enough, or do I need to spend more money and get 50 in my sample? Okay. Because that's one of the practical limitations on a lot of these studies. You got this much money. Well, I'd love to have thousands of young women in this. I'd get really good results. My randomness would narrow down and I'd get a very narrow normal curve. But you usually can't afford to run that study. And so these sample sizes end up being small due to cost. And so if you go, oh, this isn't going to really tell me anything, you might be able to go back and get them to give you more money. But if 25 is big enough, they're going to be like, no, just run it with 25. It's good enough results. So the alternative hypothesis, the 5% significance level, notice this is one-tailed. So when I calculate that confidence interval, I'm doing 90%. Okay? The confidence interval on 0 with a, is this really 0 with the standard, no, standard deviation's 2. Okay, so we'll go calculate our confidence interval. New statistics, confidence intervals. Everything we're doing is Z right now. We're using stats. My standard deviation isn't actually 2, it's 2 divided by square root of 25. Because I have, from now on, we will always be dividing by the square root of sample size. I guess I could have, square root of 25 was 5. I could have just done 2/5. Oh, no, I don't need to. Okay, never mind. It's gonna take care of it for me because it asks me for n. 0. And I would probably want to write out my work. 0 plus or minus 1.645 is the 90%, which again, 90% gives me 5 on each tail since this was one-sided. 0.05 is going to work out as a 90% on two-tailed. Confidence level, I need to change to 0.9. And I get negative 0.658 to 0.65794. I'm going to keep extra sig figs. That's the end I'm interested in. Because it was saying a significant a distance of 1. So now I'm going to calculate mine. I use my upper value of this minus my new assumed mu. A distance of 1 away would be good. Over and so I'll calculate that. 2 over square root of 25, 2/5 or 0.4. I'm just going to put that in as 0.4. And I get 0.085515. So now I'm going to do my normal CDF with that value. Distributions, normal CDF. And I get 0.196 is my probability of type 2 error. 1 minus that is my power. My power is 80.4%. So type 2 error. So I actually got a reasonable power out of this. If 1 is significant enough to be a thing, 25 was actually good enough. A little bit surprising. Standard deviation was only 2. That was a big important piece of this.
That's the standard
then you would have needed a larger sample size. Or if standard deviation was larger, a significance of 1 might not have been enough. So there's ways to increase the power. One way, when possible, increase sample size because you narrow both of your distributions, giving you less overlap. Way 2, which isn't always a great way, is increase alpha level. So if you were at a 0.01, maybe you go to a 0.05. Going from a 0.05 to a 0.1 isn't always great, but sometimes there's always trade-offs, and you have to decide what they are. So if you increase the alpha level, you've shifted this that way, which means shifting this that way, which reduces, you increase your type 1 error, but you reduce your type 2, which means you increase your power. Increase the sample size, it's just going to narrow this curve. I guess it'd be taller. That one is always the best one if you can do it. But sometimes it's very difficult to get larger sample sizes. It's hard. Another option is, and sometimes this is fine, sometimes it's not, but move this value, this 1, that we said 1 was where we said it was significant, move it further away. Maybe 2.05 really isn't too salty. It'd be fine at 2.08. We're not really starting to notice it. That was just a really over the top value. And so what the consequences of each one of these, almost always there is some consequence. Sometimes this push this value further away is the least bad one. You know, we're like, oh, that's not really enough to really care. But you want that to be a practically significant value, and you probably want it to be the closest practically significant value that makes sense. So where the chips start to be noticed being bad, where that increase in bone density really starts to actually help people later in life. The last one, which is definitely difficult, but sometimes has ways of doing it, is decrease sigma. And it might be improving the measurement process and restricting attention to subpopulations. Common ways to decrease the sigma, or decrease the variability within my population. Most of the time, that's not doable. But it has the same effect of narrowing the curve as increasing my sample size does. Okay. And I believe that is the end of chapter 2 now. Different views of statistical tests. So the distinction between tests of significance and rules for deciding between hypotheses do not lie in the calculation, but the reasoning that motivates them. So a true test of significance is just about, do I accept or reject? Or do I reject H naught or fail to reject? Do I have the evidence against this? And those are used a lot in court. A lot of times these are also used when making decisions that don't actually go to court. So in court, you're often looking at significance tests. Do I have enough evidence for this? If you're a drug company, do I have enough evidence to reject the claim that this is going to kill you? Okay. that this is going to cause blah, blah, blah in your blood that I couldn't tell you what it would be, but that's going to ruin your liver. And so you'd be looking for evidence. That's more of a significance test. With my chips, it's do I sell these or not? If I fail to reject H naught, I'm accepting H naught and going with it. If I reject H naught, I'm accepting HA, which means I throw out my batch. And so knowing the consequences of those two is big on decision analysis. With just a significance test, you're probably just testing. You don't really have to worry about the type 2 error. When you're making a decision, you've got to worry about that type 2 error and that power of how often am I accidentally selling bad chips? Okay. And the type 1 error is still relevant. So that's kind of the key to this. Yeah, you have to do the problems. And you will also find out what you don't understand and have to ask questions. Because there will be some of that. Like, oh, this makes sense. Wait, how do I apply it in this problem? What do I do again? Yeah, that's a thing.